So now we want to consider alteration method. So third chapter. So far what we have done is lots of cases what we want to do is we want to show that there is some combinatorial object with certain property. So we want to show the existence of some combinatorial object. And how we did it is that, let's say, with a good property. How we do it is that we choose a random object. And then we compute the expectation of certain random variable which measures this good property. And then if this expectation is alpha, then there exists a choice which makes this x at least alpha or at most alpha. But sometimes, this good property and this expectation can be slightly off. For example, this good property is ensuring this x to 0, but here x is small instead of just being 0. Then, with this expectation, you cannot really say that the x can become 0. Unless there are more, assumption that the x is integer and then it's smaller than 1, then you can actually check that x is always non-negative integer, and then expectation is smaller than 1, then you can say that x can be 0. But if no such assumptions are there, and this small is not really smaller than 1, it's small in other magnitude, then you cannot do this. So in those situations, what we can do is that we combine the randomness with some deterministic correction. So let's consider an example to see what I mean. So we want to prove that this Ramsey number, diagonal Ramsey number RKK, is at least k times 2 to the k over 2 over E. So before we show that this is at least square root of 2E under k times 2 to the k over 2. That was the first theorem we proved. But this says that we can actually delete this square root of 2. How do you do it? So before, when we prove this RKK is bigger than square root of 2E under k times 2 to the k over 2, what you do is you take n vertices, and then you color the edges red or blue in a random way, and then you make sure that this n is set to some number, so that with positive probability you can actually get a coloring which doesn't give us any monochromatic clique of size k. But here what we will do is we will let this n be bigger than before. So n is slightly bigger. So n is bigger than before. So that means now, the probability that we actually avoid all the monochromatic cliques here may not be positive. So there could be some monochromatic clique. but still, I mean, we can show that there are small amount, number of monochromatic click is still small. Then we can manually delete the vertices from here to kill all the monochromatic clicks and then see the remaining one. If this remaining one give you a bigger graph than before, then we actually gain. So that's our plan. So let n be a number which will be determined later. And let x be the random variable, which is the number of monochromatic clicks of size k in a random to coloring. So we color the edges of the complete graph on n vertices with 2 color. Then now what we want to do is we want to compute the expectation of x. But again, x can be decomposed into indicator random variable, where c is k vertex set. Vertex subset of k vertices. And then this is 1 or 0 if c induces monochromatic kk and 0 otherwise. Then expectation is by linearity of expectation, it's just summation of this. And there are n choose k many choices of c, and then probability that it's monochromatic is that there are k vertices, then number of edges is k choose 2. All of them are red with probability 2 to the minus k over 2, and all of them are blue with the probability same. You add them together, then you get 2 times that. So this is the expectation. So that means that there exists a coloring with at most this many monochromatic k click. And as we planned before, we delete a vertex from each monochromatic k click. So if there are one monochromatic click and another, I mean, there could be a situation that if you just delete this one, then it will kill 3. But that's a good situation. But even at the worst situation, if you delete one from each, then we can actually kill all monochromatic k click. Then we retain a graph with at least n minus how many we deleted, n choose k times 2 to the 1 minus k choose 2 vertices, but no monochromatic k clicks. So this shows that this RKK is at least n minus n choose k times 2 to the minus 1 2 to the 1 minus k choose 2 for any n. So the above logic holds for any positive integer n. So this holds, and as this is a bit not convenient to deal with, we just take a lower one which is easier to deal with. So because of this binomial coefficient is actually this. So, and we want to, what do we want to do? We want to choose n to maximize this bound. And how do we want to maximize? When a function is given and we want to maximize, the first thing we do is we take a derivative. And you take you consider this as a function of n. You take the derivative and let it equal to 0. Then times e over k times you get this. And so in order to make this happen, we want to say that 2 to the k times. So we wish to, so this suggests that taking this n to be this expression is a good choice. It's a basic calculus. But as k grows, this is, almost 1. So this is actually 1 plus little of 1 when, this is a function which goes to 0 when k goes to infinity. So we let n be an integer nearby, just ignoring this, then what we have? This is 1 over e times k times 2 to the k over 2, 1 minus 2e over k. So this is a simple calculation. So this is 1 minus 0 of 1. So which gives this lower bound. As I mentioned. So this example illustrates what's the alteration method. It's called deletion method or it's called alteration method. In this, lots of time what you do is you make some random object and then it has some small imperfection, some small structure that we wish not to be there. Then what you do is you just delete some part of it to destroy all the bad structure. Then you get what you want. And sometimes you actually take some random object and then add something. So it could called addition method, but in total you make some random object and then you alterate something to get what you want. So it's called alteration method. And by, like here, if we aim to completely, have no imperfection. So you want to completely get the two coloring with no monochromatic clicks, then this n, we put a more restriction this n on this n, so it tends to be smaller. But if we allow the imperfection, even in the small, degree, then n could become quite bigger than before. So, and this imperfection can be dealt with, by hand. So that allows us to actually, get a bigger monochromatic click here. So in lots of cases, when we want to prove some bounds, instead of just, considering it purely random object, if we make some alteration, then you actually get a better bound. So the time is a bit weird, but as the next one is actually a bit long, So we will see more examples on this alteration method in the next lecture.